Good evening. I'm John Mulcahy. I'm one of the co-interim presidents for the Carnegie Institution of Science. I've met many of you, but want to welcome you to the last of our public lectures in our spring series, and it's going to be a very, very exciting one. Before we actually get to tonight's speaker, we have some partner institutions that are involved in tonight's host. So I want to first welcome to the stage Eric Marshall from the Kavli Foundation, who's going to tell us a little bit about Kavli.
Well, I am so excited to be here with you tonight. First, I'd like to thank Dr. John Mulcahy and as well Mr. Marius Deerdahl and Dr. Øystein Hove for co-hosting this year's Kavli Prize Laureate Lecture. Now, since the Kavli Prizes were first awarded 10 years ago, an annual Kavli Prize Laureate Lecture has been held here in this Carnegie Institution as a major public lecture. This year, we are so pleased to host Dr. Rainer Weiss of MIT, one of our 2016 Kavli Prize winners in astrophysics, who's agreed to give this year's lecture. Now, Dr. Weiss won the prize for the direct detection of gravitational waves that were predicted over 100 years ago by Albert Einstein. Now, the Kavli Prizes are a partnership, as John mentioned, between the Norwegian Academy of Science and Letters, the Norwegian Ministry of Education and Research, and the Kavli Foundation. And I should mention that the Norwegian Academy is explicitly and singularly responsible for the process of requesting nominations, supporting selection committees, and also selecting and announcing the Kavli Prize winners. Now, this year's laureates represent an international nature of the prize, where more than half of the winners are Europeans, and this year, more than half the laureates are women. So Dr. Øystein Hove, General Secretary of the Norwegian Academy of Science and Letters, will provide greater context about the Kavli Prize in just a few minutes. So I'll tell you that the Kavli Prize is one of many programs of the foundation. Now, Fred Kavli, who passed away about 4 years ago, was a Norwegian-born American who had a desire to provide funding for basic science research. And in the year 2000, he created the Kavli Foundation. Now, the foundation's mission is to support and advance science for the benefit of humanity, to promote public understanding of scientific research, and to support scientists in their work in the fields of theoretical physics, astrophysics, nanoscience, and neuroscience. Now, the vision and mission of the foundation is implemented through a series of programs whose major elements are the Kavli Prizes themselves, 20 Kavli Institutes at major research universities around the world, and the Kavli Symposium meetings which advance science and public engagement. Now, the Kavli Foundation is deeply appreciative of our founder's vision and his philanthropic impulse to provide funding for science. 7 years ago, in this very auditorium, Fred Kavli said, "Science is humanity's key to secrets of nature and the universe." This is such an exciting time for science, as we are on an accelerating journey to find and understand the secrets of nature. Fred's legacy will continue into perpetuity to support basic science and to enhance the public's understanding and appreciation of science through events such as this event here tonight, designed to give more visibility and recognition to scientists and their work. So I thank you very much. And now, Secretary General Øystein Hove will provide an introduction to the Kavli Prizes. Thank you.
Thank you very much. It is an honor to join in the presentation of Professor Weiss for tonight's lecture on behalf of the three partner institutions behind the Kavli Prize. It is the Norwegian Academy of Science and Letters, which I represent, and the Kavli Foundation, and the Norwegian Ministry of Research. And to make sure that we know that Professor Weiss actually got the Kavli Prize, we have the evidence here that is from the 2016 handing over from His Royal Highness King Crown Prince Haakon the prize to the three astrophysicists, with Ray Weiss as one of them. Fred Kavli, here he is. He was born in Norway, in rural Norway, became an engineer, went to America, made a fortune on advanced technology, and became a science philanthropist. And I think it's worth noting what Eric Marshall said was his vision. Science is humanity's key to secrets of nature and the universe. This is such an exciting time for science, as we are on an accelerating journey to find and understand the secrets of nature. That can easily be said twice in a short time. This was Kavli's vision, and this vision the science academies share. That is why we are so happy to partner with the Kavli Foundation and the Norwegian government on the Kavli prizes in astrophysics, nanoscience, and neuroscience. In short, we need to know something to do something. Knowledge builds wise actions. And here we have all the winners from 2016, with the astrophysicists to the left and the other two sets of prize winners. And to close off, this is the Kavli activities. We have just announced the winners for this year. They are all listed there, with the majority as women. And so this is a teaser of the celebration week, early September in Oslo, with the governmental dinner up to the right, and we hope to repeat that. Thank you very much. And then I give the word again to John Mulcahy.
All right, thank you both for those comments. So I'm very excited about tonight's lecture. I've been excited about this all year. So let me just give you a little bit of context, and then we'll get to the main event here. So in 1687, Isaac Newton developed the theory of gravitation so remarkably predictive that it codified it into universal law. Yet Newton himself acknowledged that he did not know what caused gravity, and so he considered the theory very incomplete. Some 200 years later, Albert Einstein took up the task. After years of work, he determined, as part of the theory of general relativity, that gravity is the consequence of the warping of space-time. Over the next century, observations and experiments confirmed Einstein's theories, and Einstein and his theory assumed legendary status. There remained, however, one nagging, untested prediction, that gravitational waves were formed when two massive objects collided. Just 3 years ago, thanks to decade-long efforts of Dr. Rainer Weiss and his colleagues, that final piece of the puzzle fell into place. Dr. Weiss's work lies at the foundation of the effort. He started designing the laser interferometer gravitational wave detector, or LIGO, as most of us know it, more than 50 years ago. Together with several, was that a clap already for that? This is a remarkable accomplishment. That deserves a clap, go ahead. Together with several fellow luminaries from Caltech, and you've seen pictures of two of them, he shepherded the project forward in recognition of their monumental achievements. Dr. Weiss shared the Kavli Prize in Astrophysics with Caltech's Kip Thorne and Ronald Drever in 2016. And last year, along with Caltech's Dr. Thorne and Barry Barish, they were honored with the Nobel Prize in Physics. So, it's going to be a very long evening if we clap for everything he's done. So I just, but it is appreciated. I'm sure he appreciates it. So he's a professor emeritus of physics at MIT and an adjunct professor at Louisiana State University. Dr. Weiss received his BS degree and his PhD from MIT and joined the MIT faculty in 1964. He's not only an expert in gravitational waves, which is what we'll hear about today, he's also known for his pioneering work and pioneering measurements of the spectrum of the cosmic microwave background radiation. He was one of the co-founders and science advisors of NASA's COBE mission, which many of you remember was one of the most important astronomy missions in the 1990s, I guess. I remember I was a young student when that happened. He is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, the American Astronomical Society. In addition to the Nobel and Kavli Prize, he's also won the Gruber Cosmology Prize, the Einstein Prize of the American Physical Society, and a special breakthrough prize in theoretical physics, fundamental physics. But I want to point out Dr. Weiss, and I'm sure he'll emphasize this tonight, he'd be the first to say that the discovery of gravitational waves entailed the cooperation of many LIGO scientists around the world. This is really a team effort. And so tonight we honor not only his efforts, but the efforts of all those LIGO scientists that were involved in this incredible discovery. It really is one of the most stunning discoveries of the 21st century. So ladies and gentlemen, Rainer Weiss.
Well, thank you for coming. This is quite a collection of people here. I hope I can do you justice and make this hour interesting for you. I don't know. We'll see if it works. And something has happened already to the computer here, which is great. Didn't take long. Okay, hold on. Here we got to go back. All right, good. So first of all, I'm going to repeat a little bit of what was in the introduction. I have to. And that is, what I'll try to do in this talk is give you a little bit of the history, and you got a little bit already, but I'll do a little more. Then try to show you what a gravitational wave really is, so that you can sort of understand how one detects it. That's important, otherwise you won't understand the difficulties that were involved. I'll show you a little bit about the apparatus, and then I'll talk about the discoveries that have been made. And at the end, if I get there, I hope to show you what some of the future might look like for this field. So let me start with just what you heard. Here's Isaac Newton. And the thing that was, as I think the introduction was absolutely on the mark about what was so wonderful about Newton. Newton did something which was quite remarkable. He took something that you saw on the earth and then related it to something that you saw in the heavens. And that was brand new. And that's where the universality came from, just as you said. And the thing is that here is Newton's equation, which we teach in high school, and we also then talk about it later in college. And what it is, it's a relationship between a force between two objects one has a mass m1, the other one has a mass m2. That's a constant. It's not terribly important, but it's a small number. And then the force gets smaller as the distance squared between the two objects. In other words, the further the objects are apart, the smaller is the force. And it turns out it's a remarkably good relationship. It tells you for almost all the things in the solar system how they operate. It works for the space program. It doesn't quite work for the planet Mercury. That was a thing, and we'll talk about that a little. It's a little bit of an error that comes into it, which, by the way, plays a very significant role in a minute. The other thing it doesn't do, and this is where Einstein came into this, was it has no way of talking about how news in a gravitational situation goes from one place to another. In other words, if you suddenly remove the sun, just pluck the sun away, it would take you about 9 minutes for your eyes to see that. You don't know it, but if somebody told you, yep, somebody took the sun away, it takes 9 minutes from that act to get to you to see that the sun is no longer there. On the other hand, if people interpret Newton's theory, and we're going around the sun, here's the sun, let's say, and you're going around the sun in an orbit, and what should happen is if you pluck the sun away, the fact is that you would no longer be held by the sun to it, and you would go off on a tangent. You wouldn't continue on around the circle. You would go off on a tangent because that force is gone. And in Newton's theory, at least the way it was interpreted, that happens instantaneously. And Einstein already knew after 1905 that the fastest any kind of information can go, or anything with any kind of mass can go, is the velocity of light. So that's one of the problems, and that, by the way, does turn out to be the gravitational wave. So Newton works for everything, but it doesn't work so well for some very subtle things, and it gets more and more problematic as you look at more of them. So here's Albert. And unfortunately, this is a little bit iconoclastic, this thing. Albert was not this old when he came up with this equation. Okay? Einstein came up with this in about 1915 after an enormous struggle. And he came to the Kaiser Wilhelm Society in Berlin at Planck's behest. And Planck was very upset when he heard that Einstein wanted to work on gravity, because he thought gravity was a well-understood thing. He was hoping Einstein would work on quantum theory or some of the modern things that were going on. But Einstein had in his mind already that there was something fundamental that had to be fixed. And his idea is represented by this equation. I'm not going to describe the equation to you in mathematical terms. I just want to tell you what that equation says. What that equation says, that this thing over here is the geometry of space and how time flows. Both time and space are in this equation, and they are determined by, this is just 8 pi, that's a standard thing. What they're determined by the distribution of matter and energy that is around. In other words, matter and energy determine the geometry of space and the flow of time. And let me try to show you this in a picture. Again, this is only intuitive. I can't give you the full characterization. These equations are enormously difficult to solve, by the way. But here is a sort of picture, and let me start by asking you, how many of you remember what a jungle gym looks like? Yeah, well, most of you know what a jungle gym is. It's a bunch of bars you've laid out, the kids play in it, and it has bars that are in the horizontal direction, in the X, they have bars in the Y direction, Y in the Z direction, and you have places where all these bars intersect. I want you to imagine that, and now do the following thing. Take a cut through the jungle gym. So that's what this is, a cut through the jungle gym, a two-dimensional cut through the jungle gym, okay? And so now you notice that everything is quite regularly spaced out here. This is where the jungle gym still behaves like it does. But here, you've plunked into this system the sun, which is right there. And that has mass and energy. And it's distorted the space. And it's made it so that it curves. And here's a little effect that's the same from the Earth. There's a little one. And so now, what the theory has, it's not complete because I haven't completed the picture. There's one more thing you have to know. And that is that each one of these intersections has a clock on it. Now, I didn't draw them in because it's complicated. Too many clocks to draw. Okay? But imagine each point here having a clock. And what happens if you synchronize those clocks? And that means you walk around with a clock in your pocket and you go to each one of the clocks that's in this picture and set them up so they are reading the same time as the one in your pocket. Okay? You can't take a photograph of a thing like that and establish that they have the same time, because the distant clocks will look like an earlier time than the ones that are near you, because it takes light to get some time to get to your camera. And the further are they away, the more that clock will not look like it's keeping the right time. So you have to go synchronize them all by going to them. And if you've done that, you'll find out an interesting thing, and that's unfortunately not in this picture. The clocks out here all read the same time, and they run a little faster than the clocks where there have been distortions in space and time. In other words, one of the things that's part of the Einstein theory is that time also is dependent on, as in that equation says, on the distribution of matter and energy. And clocks that are in a place where gravity is strong run more slowly than clocks that are far away from masses. And with those two things, that space gets distorted and time gets distorted by putting matter in it, you have a completely new way of looking at gravity. And and John Wheeler had he's a guy at Princeton who sort of became sort of the ambassador for relativity in our epoch. He said, look, matter distorts space and time, but then space tells matter how to move. And the final statement in this thing is that matter will move along those paths that are the minimum in time and space. And I won't go any further than that. In other words, you have completely eliminated the gravitational force. It's not there anymore. Now, that theory explained the orbit of Mercury and the trouble with the planet orbit of Mercury was that when you isolate Mercury, separate it from all the other planets in the system, and try to solve for its motion, it makes an ellipse. The ellipse, here's the sun again, let's say, in the front of you, right in the middle of you, and it makes an ellipse. And that ellipse, if it's Newton's theory, would stay absolutely pointing the same way forever. But it doesn't do that. It turns out, even when you correct for all the other planets, it goes in a little rosette pattern, that ellipse. It takes many, many centuries to do that, but it does. That ellipse doesn't maintain its axis. And when Einstein discovered that his equations predicted that, he couldn't sleep for a week. No, it was really, this really quite complicated new theory. Immediately when he applied it, was able to solve the problem of Mercury. Other people were trying to look for another planet. There's a book out about that, Vulcan. I don't know if you know the book. So during about the end of the 1800s, people were looking for a planet that might explain that rosette pattern of Mercury, and they couldn't find it. It would have been the planet that lies between Mercury and the sun. Very hard to see, because you'd be blinded by the sun all the time. But anyway, that wasn't there, and you didn't need it. Einstein showed it wasn't necessary. So here then is a gravitational wave, and I'll describe first what it does. We'll get to this picture in a second. But the important thing is, what are the sources of gravitational waves? They're accelerating masses that get accelerated. For example, you mentioned it in your introduction. Two objects like two trains hitting each other. That will make gravitational waves. Or two objects that are going around each other. Orbiting objects will do that. Spherically symmetric expansions. Let's say you take a balloon and blow it up and then let it collapse again. Balloon blows up, spherically symmetric. They will not radiate gravitational waves. And that's a mistake that Einstein made in his 1916 paper, which he had to correct in his 1918 paper. So Einstein makes mistakes. In fact, it's kind of fun. When you look at the 1918 paper, he says, through a regrettable arithmetic mistake. Okay? I have come up with the wrong answer, and now I have it right. Well, it turns out it wasn't a regrettable arithmetic. It was a conceptual error, okay? But he couldn't quite bring himself to say that. Okay, so now here's what gravitational waves do, and the kinematics. This means how do they move? Einstein predicted they would move at the velocity of light. As you will learn in this talk, if you don't know it already, we now know as a fact that gravitational waves travel at the speed of light to better than a part in 10 to the 15. Well, I'll show you that when we get toward the results of what have come from this research. The other thing is that this is more complicated. They are transverse waves. What does that mean? It means that the wave, and this is the wave that is going to be generated in a minute, is coming, the wave you're going to be witnessing is one that comes out of the screen or goes into the screen. And it does its stuff, it does its things, it does its dirty work perpendicular to the direction of motion. That's what transverse means. And so let me now start this thing moving, and you'll see what a gravitational wave does. If you can see this red, I don't know if you can see it, but there's a red marker. That's where you are standing, right there. That's you. And now let me turn this on. I hope it turns on and does what it's supposed to. Yep, it does. It makes you a little dizzy when you look at it, but just bear with it. Okay, now you'll notice a couple of things. That's you. You're not moving. And let's take the spots that are, these spots are moving away from each other, where the ones vertically are moving toward each other, and it keeps changing direction. So there's a squeezing of space in one perpendicular direction, and expansion of space in the other. I hope you can see that. This is an oscillating wave. It keeps changing which way it is, right? So that's one property. It's a stretch in one direction, squeezing in the other. But there's another property which is very important. Well, you'll notice, let's look at this, you again. Here you are, and look at this spot that's the furthest from you, and the one that's furthest from you. They're moving a lot. This guy and that guy are moving a lot. But these guys near you are not moving very much. And that is a specific pattern. And you do the same thing. If you went home and, I guess you need one of your kids or somebody to hold it while you make marks on a rubber band. Make marks every 1/8 of an inch on a rubber band and pull it. You'll see that's exactly what that motion is. It's a motion of, at any one instant, it's the strain, that's the change in position of two spots, divided by their separation, is the same for every dot in the place. Okay? It's a strain pattern, and the strain pattern is negative in one direction and positive in the other, and it keeps flipping. So the thing that is the quantity in the gravitational wave, that is the thing that does interact with objects, is that the strain in space is what's going on. That's the property that makes the gravitational wave detectable. Okay? Now, the very first people not to see this directly were Hulse and Taylor. Hulse was a graduate student. And they were both of them were at the University of Massachusetts at the time. Hulse was a graduate student. Joe Taylor was a professor there. He then became a professor. They both moved to Princeton. And this is the discovery they made. It was really quite spectacular. This is not a direct detection, but they were the first people to ever really get evidence that there were gravitational waves and that they carried energy. But it was inferential. Okay? So what did they discover? They discovered, the discovery was that they heard a star which was going at making pulses at about 17 times a second. So, brrr, like that. And that star wasn't steady. They didn't see anything. They couldn't see the star, but they heard it in their radio telescope. And what they noticed is sometimes, if you imagine the radio telescope here, imagine that this is the model they made of it. It was two stars. These are called neutron stars. They're about the mass of the sun, and they're only the size of Washington, D.C. about. They're tiny, and they have a density. It was a density of nuclear matter, enormous density. A teaspoon of it, you couldn't lift a teaspoon of it. The whole room, everybody pulling together, couldn't pull up a teaspoon of it. Just couldn't do it. It's amazingly dense stuff. So these are stars that they're spinning. And this one is spinning, and it puts out a pulse every time, 17 times a second. And it goes a little fast. Let's imagine the antennas right here. When this thing is moving, they're moving around each other. When that pulsing star is moving toward the detector, it goes a little faster. And when it's moving away from the detector, it's going a little slower. That's the rate of pulsing. So they had a wonderful experimental laboratory in the universe where they could measure all sorts of things that had to do with gravity. And what they measured all sorts of corrections. But this is the picture that is most important. What they did is they watched this system for, an epoch. This is epoch, 1973. The picture ends at 2000. And what they watched is how long it took for the system to make one orbit. And that getting shorter and shorter and shorter and shorter. These are negative changes. And so the dots that are in this picture are their data. This is the period of the orbit. Got shorter and shorter. These were going around each other, and they were clearly getting closer to each other and going faster. And why was that happening? If you now go to the theory and say, go to Einstein's 2018 equations and his 1918 equations and his 1915 equations, you can get a model, solve for the motion of two objects, and you are seeing the change of energy of that system due to the radiation of gravitational waves. And that's what they saw. They saw this getting closer and closer, and this is the theoretical curve you would get just using the Einstein equations. It's not a fit. They calculated just the way it would go. And it turns out that was the very first measurement, indirect measurement of gravitational waves, a system that was accelerating, losing energy to gravitational waves. Okay? So that was a big discovery. It won the Nobel Prize, by the way, in, I think, 2003, among other things that they discovered. Now, the first person to try to actually measure gravitational waves directly was Joseph Weber. And he did this, and this is a picture of Joe. He was a professor not very far from here. If you take the metro, you'll get to the place. It's the University of Maryland. And he had the idea that one could measure gravitational waves, that pattern that I showed you with the dots. He wanted to see that happen in reality in a great big aluminum bar. There he is putting strain gauges. These are the devices that measure the stretching of this aluminum bar. And this is a huge piece of aluminum, bigger than he is. And he was then the first to try to directly measure gravitational waves. And to his misfortune, he discovered them. Okay? What happened was that he built 3 of these bars. We built many of them, but he had one here not far from, right in College Park. And he had 2 in College Park. One in his lab, another one in a golf course not too far from the university. And then he had one in Chicago at the Argonne Laboratories in Chicago, so a big, goodly distance away. And what he saw was, he says, he was seeing coincident pulses in these things, typically 3 or 4 a day. And he interpreted that as gravitational waves that were coming from the center of our galaxy, doing just what that picture that I showed you, what the dots were doing in that picture, to that bar. And it turns out that, I wish he had been right, we now know, and many, when you make a claim like that, when you claim something in the literature that you have, and he made a claim, he says, here is, in 1969, he wrote a paper, here is evidence for the direct detection of gravitational waves. A lot of other people, when they see this experiment, it doesn't look like such a hard thing to do, and they tried it themselves. And nobody saw it. Nobody in the world saw it. And that was a big problem. And now we know why nobody else saw it, because these kind of detectors, as we now know what the strain that you have to be able to measure, is a strain of 10 to the minus 21. We'll get to that in a minute. By the way, how many of you are mystified when I say a number like 10 to the minus 21? Is that, please be honest with me, I will. Some of you. Okay, let me just say what it is. It's a nice way of writing powers of 10. Are a nice way to talk about big and small things. But the other idea is it's a nice way of writing a very small number and a very big number by using, let me give you a number. Let's say you would try to write the number 1,000, okay? Well, the way you can write up 1,000, you could write it as 1000, okay? But you can also write it as 10 times 10 times 10. That's 10 times 10 times 10. That's 3 times 10. So 10 to the power 3, okay? And so you can write every number that way. I mean, every number power of 10. It's a nice way. Now, when you write something like 1,000th.001, it's the same as putting it make a fraction. Number 1 in the numerator and 10 times 10 times 10 in the denominator. Now, this is in the denominator. So it's 10 to the minus 3. It's a minus tells you whether it's in the numerator or the denominator. So 10 to the minus 3 is just an elegant way of writing 0.001. Okay? Let's not make it more complicated than that. You don't need more than that right now. Okay. So I'm going to have to use that, otherwise I can't talk to you. Okay. All right. So, so the number that now, and this is the, let me show you the next idea. This is the idea that actually made the measurement. And I think given what you now know, I hope you can understand this. So before I start this is a little animation. But this is a laser. Of course, it isn't a laser. That's a piece of junk. But the thing is, think of that as a laser. Think of this. This is, by the way, a beam splitter. This is a device that you are very familiar with. When you look into a mirror, when you look into a plate glass, look into a glass, sometimes you see a reflection, but you can also look into the room that you're looking into. So there's both a reflection. So laser light, you'll see this in a minute, will hit this partial mirror, and half of the light will be reflected to this mirror. The other half of the light will go through it and go to that mirror. And they come back again, both of the beams will come back, and they go to this detector. And now I want to start this and tell you what this is all about. So, by the way, if you want to relate to the picture that I showed you with the dots, this is the little red square, that's you. And these are the distant dots in the 2 dimensions, and the gravitational wave, which we're going to talk about, will be coming down on this thing. Okay? It's coming down on the plane of that. So let me start this animation. Okay, so wherever you see red, there is light. And then you see the wave that makes the light. That's the electric field that makes the light. And that is a way of keeping track of the phase of the light. And you'll see that right now, the light is spending equal times in these. These are equal distances. And no light gets to the photodetector. The 2 waves cancel each other. And now what comes down is you push this mirror in and push that one out, and it changes, makes the paths no longer equal, and light does go to the photodetector. You see that? That is the basic idea behind the other way of making measurements of the gravitational waves. In other words, you set a trap which makes it so that you have light being equal paths in these 2 arms. That gets spoiled by the gravitational wave coming down, and you will detect light out of the photodetector only when there's a gravitational wave coming down and destroying the symmetry of that. That's the basic idea of LIGO. Now comes the bad news, okay? And the bad news is, this is Kip Thorne, by the way. who had a very effective group of people worrying about the theory behind making gravitational waves. What kind of sources would there be in the universe that would make them? And very early in the game, after Weber, this is after Weber, it's probably 10 years after Weber, it became quite clear to everybody that H is the strain. Here's again the definition of the strain. That's a change in length divided by the separation. That had to be, anything in nature would make a strain that was only as large or smaller than 10 to the minus 21. So again, so that I remind you what that is, that's a decimal point and a 0, at 20 zeros and then a 1. 0.000, 20 times, then a 1. I prefer to write it as 10 to the minus 21. Now, if you take a 4-kilometer system like what LIGO turned out to be in the end, you make the arms 4 kilometers long, you wind up with a change in length at the ends of only 4 times 10 to the minus 18 meters. And that is about 1,000th the size of a proton. In other words, here you have a thing where you're measuring 1,000th of a size of a proton over 4 kilometers. And that's a challenge. Okay? And it comes in 2 challenges. There come 2 pieces of that challenge. And that's why, as you said, it took a long time. Okay? It took 40 years to develop the technology to do that, and by a lot of people. And one way to write it in the nature of the challenge is that the change in length is, if you want to measure the position of the mirror to that strain that's necessary, you're going to measure 10 to the minus 12 of a wavelength of light. The light that you're using has a certain size, and you're going to go 1,000,000th times 1,000,000th of the wavelength of light to make that measurement. That turned out to be hard, but not as hard as the second one. This says that even if you had those mirrors and you had the technique for doing it, those mirrors shouldn't wiggle on their own more than 10 to the minus 12 of the amount that you're shaking in this room right now. Everybody in this room is wiggling up and down by 10 to the minus 6 meters. Why? Because the Earth is shaking that much. So you have 2 big factors that you have to solve, and this one is much harder than that one. And let me show you some ways of this thing. I'm going to skip this next slide because I don't have the time. Here's the way we solved the problem of making the very small measurements with light. That's the first problem, that 10 to the minus 12 of a wavelength of light. So now this is very much like the picture you saw, but now let me show you what's in it. There's the laser again. Here's the beam splitter, that thing in the middle where you were standing in that picture with the dots. And there's that distant mirror, and there's that distant mirror. So those are the major components, just like that animation had. But new things have been added to this. One of them is that you see some additional partial mirrors here, these 2. These are mirrors that are partially reflecting, and what they do is they make the light come in and they bounce the light something like 300 times back and forth before the light comes out again. That's one way of thinking about it. So each one of these arms has now 300 times more hits on the mirror, has 300 better chances of measuring the gravitational wave, or you can think of this 300 times longer. Either way, it's up to you. And so the same thing happens in both of these arms. And again, if you do it so that there's an equal time spent by the light in this arm and that arm, no light will go to the photodetector. That's the same story as we had with before. And all the light will now go back to, all the light that's coming into the interferometer will come back to the laser. And that's a bad business. The laser doesn't like that. And so here you add another mirror. And this is a mirror again, which is partially transmitting. And now here, let me walk you through that one. This mirror, or partial mirror, does the following. There'll be light coming out of the laser, hits the mirror, and bounces off that mirror. So there's one path that hits that mirror, bounces, and come off again. But the rest of the light goes through it. Then the light coming back from the interferometer, or that device which is called the interferometer, none of it's going to the photodetector. It's all coming back to the laser, will come through this mirror, and now you have 2 beams, one that bounced off this thing and another one that went through it. And what you do is you, again, do the same trick. You make them cancel each other interferometrically. So now what you've done by doing that is you have no light coming back into the laser, and you have, let's say the laser has 10 watts in it. By doing this, you build up the light in this little cavity so that you might have 500 watts of light in this arm, inside this. And in these, you might have something like 200 kilowatts of light, maybe even half a megawatt of light. So you've really built up the light tremendously, and that allows you to interrogate the position of those mirrors so much more carefully. So that's how we solved the optics problem, or the problem of the position. I don't think I want to go into that one. Okay. So let me just a second. I want to go back and establish what I've done here. Yeah, okay. And now here is the LIGO, what was built. We built 2 of these. There's one in Louisiana, and there's one in Hanford, Washington. There are others. There's another instrument that the Italians and the French built, which is in Italy, near Pisa. And then there's a research instrument that is run by the Germans and the Scots. This is only 600 meters long. And what's planned for the future, and I'll explain why at the end of the talk, there's one being planned in Japan that's being built inside of a mountain. And I'll explain why that's being built. And there's another one being built in India. And the reason for all of these detectors will become obvious at the end of the talk when I talk about trying to identify where on the sky a source might be. We need multiple detectors to do that. But that's for the future. Right now, the next thing I'm going to be talking about are the work that was done primarily by these 2 detectors. And so let me give you a little picture. This is a little travel log of LIGO. This is looking down on that system of 4-kilometer arms, interferometric arms, in Louisiana. There are trees in Louisiana. And that's Hanford. That's a desert. And here is a big concrete cover that covers the vacuum tubes. That was in Hanford. Now this is the one in Louisiana. Here's what the tube that carries the laser beams are. It's about 4 feet in diameter. And here's a standard laser table. You'll find that in many laboratories right here in Washington. And here is the control room for the Livingston interferometer and people learning how to lock the interferometer. Okay. I just want to show you this because this is kind of fun. I'm not going to tell you anything, but that's a statement of progress. Let me tell you what went on in here. This is a picture of frequency and sensitivity. The sensitivity gets better. You get smaller and smaller motions that you can measure as you go down in this picture. And the only reason I'm showing you this is it shows you something which was very important to us. That over the years that we were working on this thing with LIGO, starting in about 2000, we start with these curves, and time, epoch, progresses as you go down. And we made an enormous improvement over the years of making it better and better and better. And we finally got to, this is about where we were in around 2007, and we got down to what's called design sensitivity, which is the calculation you would make for how well this instrument should work, and that's that dotted line. We didn't quite make it at these low frequencies. Here, for example, is 100 hertz. That sort of middle C on the piano is about right there. But we did very well, and because we made a clean non-detection, in other words, we didn't detect any gravitational waves, but we understood the instrument well enough, we were able to convince our sponsors that we should go ahead and build an advanced version of this detector. I just want to show you this, because that was an important step in the process of making the detection. We built the initial detector, much like what you saw in that picture, but then we started making changes in it that actually made it so that we got enough sensitivity to make the detection. And here are the steps that were taken. I won't go through pictures again, except the big thing now was we had to solve the problem of not having the mirror move because of the earth shaking. That was the big step forward. And so one way of doing it is, this was incorporated in advanced LIGO, was here's the earth, and this is a pendulum. Let's say this is a spring attached to the earth that's shaking at 10⁻⁶ meters, and this is a pendulum, and that has another pendulum hanging from it, and another pendulum hanging from it, and finally that very precious mirror hanging from it, all 4 of these in series. Let me show you what a pendulum does. I just have to do it with my hands. If you have, let's say, here's the earth shaking the top of the pendulum, and here is the bob on the pendulum. You can do this at home. Easy thing for you to do. If you move very slowly, the pendulum moves with you. That's what happens. But if you move fast, the pendulum doesn't move. And you can try that. There's just a rope and a piece of mass. Just try it. You'll see it's a very good vibration isolator at certain frequencies. And that was critical. And then the other thing is a thing which I only will allude to what this is that here's that pendulum hanging from a gadget up here, which does the following. I won't describe it any more than to say it's something that you're familiar with in a different setting. How many of you when you fly in an airplane, put noise-suppressing headphones on? Well, a lot of you do that. Okay, that's the same idea. There's a microphone in the headset that measures the noise in the airplane, and that feeds it in an inverted way into the headset so you don't hear it anymore. That's what happens. It's a negative feedback system. And so what happens is you did the same thing here with seismometers. That allows you, by the way, this idea, although I'm not describing it, you can ask me questions about it, is actually useful to people who are making microscopes or trying to do lithography on semiconductors. It's a very useful thing to do. And it's one of the few products of LIGO that is applicable to other people, okay? And useful, okay? So anyway, here then is the discovery. And this was... So let me walk you through this a little bit. What this is time, and what you see on the y-axis is the strain, and you can see that there's 10 to the minus 21. This is sort of 1 times 10 to the minus 21. And this is the signal that we saw in Livingston, in Louisiana. This is junk. All that's junk, but something begins to come out of the junk, and it's that, and it gets more and more coherent, and then this is junk again. Now, very similar thing is happening in Hanford. That's why we had to have 2 of these. And this is junk again, but again, something comes out of that noise, and you can now superpose those signals on top of each other. And you have to do something elegant when you superpose them. You have to take one of the signals and shift it by 7/1000th of a second. Why? The reason is the signal hit Louisiana first. Okay, and it went through the Earth and then hit Hanford. And that was the first evidence we really had that there was time taken by a gravitational wave going from Louisiana to Washington State. Not Washington, D.C., Washington State. And so what happens is you put them on top of each other, you have to slide them, and now you can see that this is sort of incoherent there, but these become more and more coherent. And then this is junk again. And this was our very first detection. I want to show it to you in another way. And you can also present it this way, which is another way to do it, and that's why it's called a chirp. This is, again, the time axis. And here now, what's represented, this is the waveform you just saw. This is this is the one in Livingston, that's the same waveform at Hanford. But now there's another picture, in the picture there's another thing, which is the frequencies, the sounds that are in this waveform. And for example, that's what this picture gives, and that picture right there gives. And so what here, for example, is 32 hertz, sort of the bottom of the piano. And here is middle C on the piano, okay? And what this is it's like you take a glissando. You take your finger and run it along the piano, make a glissando. And let me play it for you. And you'll see it's not very interesting. Now what you heard there was the noise in the instrument, and then every once in a while, boop, boop, like that, okay? Well, okay, so we try to make it a little better. This is fudging a little. Okay? So that's that chirp, and it starts at a low frequency and ends and that is, what is it? And we found out what it was, and there is another very important thing that came of the field, which is that just at the time when LIGO was beginning to make these detections, as we will see, this is the idea of what we were seeing. And people were doing numerical solutions of the Einstein equation. That equation I showed you. People were actually able to finally get a computer to solve an Einstein equation, the Einstein equations. Took almost as long as it make the instrument to get that happen. It was not easy, and because the theory is difficult, and the complicated word for it is the computers kept blowing up. What happened is they just got to a point when they made a black hole, and that was the end of it. They didn't know what to do with it, and so you had to figure out ways to not let them blow up, and that was very difficult. So here is what you're about to see now is what this signal comes from. And it is very much like the representation I showed you when I showed you the jungle gym. So let me see, let's hope it works. Yeah. What it is the Einstein, the solution, a computer solution, not an artist's rendering, a real solution of two black holes going around each other, each one weighing about 30 solar masses. And here is the jungle gym. And now the colors represent time. And when it's green, time goes fast. But when it's red or black, when it's black, time is stopped. And you can see the curvature of space. And these little arrows sort of give you the tension that's in space due to the strain that's induced. So this is keeping up with it. It'll slow down in a minute. You can see a real storm being generated in the geometry of space and time. But both are sort of exciting. What happens here is you'll see that, here now it slows down. And you can see already mountains, little mountains being made. Really sharp curvature changes. Here, the time went to hell right there. And so it is unbelievable what's going on in space and time. And as these two black holes collide, and then they form a new black hole, everything calms down. And the gravitational waves, they go off, and that's all that's left of it. And those gravitational waves, this whole thing took place at about 1 billion years away from us. Okay, that the time it takes light to go 1 billion years is about where this took place. And that was that big discovery in 2015. And and here is a very cute thing that happened. I was giving in fact, some of you have Janna Levin's book. I was going to give a talk at Janna Levin's Institute, and I was in the subway in New York, and let me read you what this thing on the right says. It says, scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. Now, I was sitting sort of being tired and dreamy in the New York City subway. I saw the light. I couldn't believe it when I read that, okay? And then this is very shortly after the press release. This is a picture that came out of the New Yorker. It had two birds sitting on a branch, and this guy saying to that guy, "Was that you I heard just now, or was it two black holes colliding?" You see. See, suddenly, I mean, this is sort of, we mentioned this in some interview today, how interesting the public was drawn into this thing much more than many other discoveries that have been made in science. And I think it has to do with Einstein being a very popular figure. It also has to, you and I were talking about that. And then it also has to do with that most kids know about black holes. They're terrified of them. And everybody knows black holes. They know they eat you. So anyway, sort of remarkable that this sort of happened. Anyway, we quickly after that saw more black holes. I won't go into this. These are just more pictures. The one we were just talking about, this again, these pictures, time and strain. And this is the guy we were talking about. Christmas, just before we even announced, we saw this guy. These are the masses. The masses of the first one was 36 masses, 29, and 3 masses disappeared into gravitational waves. 3 solar masses. It's a huge amount of energy disappeared. Anyway, this is all the black holes we had by January 4th of 2017. This was also seen by others. And now let me get to that. And this is the importance where I'm trying to show you why it's important to have more detectors. And the thing is, this was seen not a big, it's again 30 solar masses, and it's not a beautiful event. It wasn't as good signal and noise as the others, but here are the spectra and there are the waveforms. This is now Livingston, and here now, and that's Hanford. But now here is Virgo. And they're not as good as, their detector wasn't yet tuned up right, but they saw it, and what that allowed is, here's a picture of the sky, and the uncertainty in the position of the sky with just LIGO alone is given by this banana here. Okay, why is that? We don't have any way of pointing these detectors. What we can do is we can say, look, the antenna in Louisiana saw it first, and then the time difference between the two signals is all we have. And that tells you a great circle on the sky where the source might be. If you have another detector, you can compare another, let's say Louisiana with Pisa. Virgo, the Virgo detector. You have another pair and so forth. You have 3 pairs. And then there will be intersections on that circle. And that's what's happening here. You add Virgo to this, and it gets this is an error circle of thousands of square degrees. This is an error bar of about 30 square degrees. That's dramatically different when you tell an astronomer who has, like the Carnegie Institution has, say, go look in that part of the sky for this event. And you tell them to the 1,000 square degrees, they laugh you off. But if you tell them to 30 degrees, they'll skulk a little bit. I mean, what they really would like is a better position, because they would love to know something on at least much smaller than the size of the moon. Well, we're not quite there yet. But this is the way to become part of astronomy. Okay, so let me go on. And here are all the black holes. I don't think I want to waste time. This is the next and most significant event that has happened in this business. What this is this happened in August of last year, 2017. What it is this has a lot of pieces of story to it, and it's one of the more interesting stories. What this is the same thing you saw before, namely this is time, but now the time goes for much longer. Here it's 10 seconds, well, minus 10 seconds. This is 10 seconds from here to there. And here again is the signal that you hear as how you would hear it. And I'll play it for you in a second. But this is the middle C is again around here, but this goes a little higher. And here is a very coherent signal that was seen actually by all 3 detectors. Well, let me be honest with you. It was seen by LIGO, it's 2 detectors, and not seen by Virgo. But there was a good reason why it was not seen by Virgo, because it was not in the antenna pattern of Virgo. But by not seeing it at Virgo, people were able, as I'll show you in a second, to pin down where this was. It's sort of a little obtuse story, but okay. So now, let me play this for you. You'll see this sounds entirely different than this other thing. This is now 2 neutron stars colliding. And let me see if I can get to, oh my. There it is. So, okay, that's a real chirp. And that's what that is, by the way, the same thing that Hulse Taylor would have, if Hulse Taylor, that guy, the people who saw the two pulsars going around each other and did all this first measurements of gravitational waves, had their thing, had we been there 10 to the 8 years, 100 million years from now, their system would have done this. In other words, now, this thing was really quite remarkable because it did something else. It was seen also by a gamma ray telescope in space, the Fermi telescope. And here's the endpoint of the things collide. By the way, the 2 neutron stars don't collide at 400 hertz. Our detector is not good enough to see this. They would have come, if this had been continued on that curve, at about 1 kilohertz is where they hit. So it's 3 times further distant than that. But you can interpret where that happens. It's very quick. And here's that line that would have been the endpoint of the collision of those 2 neutron stars. And here, lo and behold, 1.7 seconds after the collision that we would have seen, or we almost saw at the end, there they saw a pulse. They also saw another one in a different detector, which is on the same spacecraft, and then a not as big gamma ray detector also saw something there. And now what this is sort of really quite remarkable. This is the place where we really established that gravitational waves travel with the velocity of light. Because this source is 40 million light years away, and it comes in at the same time to within 2 seconds. And you do the arithmetic, and you'll get that the velocity of gravitational waves and the velocity of light are the same to 1 part in 10 to the 15. So why there might very well be, and people have modeled now why there was this 2-second delay. They think that was not there. It's not due to the propagation differences of the 2 waves. It's due to the fact that it took a while for that explosion of the 2 neutron stars to make enough light and make enough gamma rays so that you saw this in the gamma ray telescope. So I mean, as far as we're concerned, that we now know that gravitational waves are so close to the velocity of light that it's not worth making a big fuss about anymore. And what else was seen? This is that thing that really was sort of remarkable. Because here sort of this tells you the story. Here is the uncertainty of the LIGO alone, these bananas. Again, this is a picture of the sky. And then there's a piece right here from that timing. And when you add Virgo's non-detection to it, because they should have seen it, you reduce the thing to this size. And that then told people where to look. And here is, for example, the uncertainty that comes from the gamma ray telescope. It's bigger than the uncertainty right now from the gravitational wave. And so what happens is people very quickly on the ground went and looked in this little error circle, and lo and behold, look what they found. This is a place they were looking at sort of 20 days before the collision of the two neutron stars. And there are the two stars, and this is a galaxy. The galaxy is, those of you who care, is NGC 4493, a nondescript, not very remarkable galaxy, but 40 million light years away. And this is what they saw after. So here are those same stars, here's that galaxy, and lo and behold, right there is a new thing that wasn't in the picture taken 20 days before. So now that got very exciting for everybody. So a whole, probably 300 observers on the ground went and trained their telescopes onto this thing, and they found out a tremendous amount of stuff. And what it is they saw something called a kilonova. And what it is two neutron stars smashing into each other, eventually, we think, making a black hole. And that the gamma ray burst isn't quite on axis because it comes off. This is where the gamma ray telescope was relative to how this collision took place. And it turns out, now what did this do? It did a lot of stuff. And it effectively was seen by all the different versions of looking at the sky. It was seen by radio astronomers, but it was seen by visible and infrared, it was seen by gamma rays and X-rays, and obviously gravitational waves. So this is now called multi-messenger astronomy, and is a big code word for a big new way of looking at the universe, namely using gravitational waves of really getting at it. And what did it solved two problems. Two things came out of this, out of this one measurement, two things came out that were really puzzles for years and years. One was, were gamma ray bursts, which have been seen for years and years. For many years, people thought gamma ray bursts were the Russians not obeying the test ban treaty. No, I mean, that was serious. I mean, under more paranoid regimes than we have now. Well, I shouldn't have said that. Okay. There were people thinking that Russians were putting bombs, atomic bombs, testing bombs behind the moon, and you couldn't see them. And that's why gamma ray telescopes were put up, and they found these pulses, which happen every day. And the people then eventually found, and now we know, people had guessed at this, that it really is two neutron stars hitting each other. That's where, and what comes of that is something which was also not known, and this is a little story to the side. I'm showing you a periodic table here. What it is, we never knew exactly where all the heavy elements came from. I mean, when you look at any astronomy book or any book on the origins of the Earth or the origins of the universe, you'll find out that people know where hydrogen was made and where helium was made. That was part of the big explosion that made the universe. It took years to figure out that all the other elements were made inside and cooked in the ovens of stars. And those came into the being as they got blown into the interstellar world by supernova. But they couldn't get past about the heaviest, past iron. They got somewhere past iron. That's up in the periodic table someplace. It's up, it's right in here someplace. Okay, I didn't point to the right. It's Fe, and you'll find it. There it is, right there. Okay, so what happens is people could not figure out how you made things after lanthanum, which is right here. And all the sorts of things like platinum and gold and mercury and lead, all those things were not made in stars, could not be. The cooking times weren't long enough. And so now we know where they came from. They come from neutron star collisions all over the universe. It's another really remarkable thing that came from that. Now, that thing I just told you isn't as solid as some of the other things I told you. I'll tell you why. If you look carefully at the papers, you'll see that they didn't identify lines. They identified models that predicted this, and models that made the same kind of color as what was measured by the astronomers. I wish they had seen lines, and maybe in the future they will. You know, real lines from the individual atoms that are these heavy atoms. Okay, I think what I want to do is, we're getting near the point where I should stop. I want to show you one other picture, and then I'll give you the last. This is not the last slide, there's one more. What this is a picture just so you know where we're heading. And I want to tell you something. This is, again, one of these pictures where you have frequency this way and sensitivity. Sensitivity is getting better and better as you go down in this picture. So the further down in this picture you are, the better is the further you can look and the more sources you can see. And let me show you where we are right now. The sensitivity of LIGO that we measure is this line as a function of frequency. And where we want to be, the design sensitivity, when you design it, we should be here, the green line. So we have a puzzle, and that's a puzzle we're working on right now. Why is the performance of the instrument not at the green line. That's our first worry right now. And we're busy trying to figure that out. But we already have plans because we think we know enough. We can think of an instrument we can put in the same facilities we have now that does this well. That's something we can do near term. Probably the very best facility, the best instrument we can stick in would be down here. And that's something people are thinking about developing technology for. And in Europe and the United States, we're thinking of how can you finally take this field and go into something called cosmology. Right now we're looking at individual sources. Where, for example, we'd love to know where the black holes come from. We'd love to know, was there initial time when there were no black holes? Things like that. But right now, if you want to do cosmology, which is the science of the whole universe, you have got to, if you want to use gravitational waves as a way of doing something with that, you have to make new instruments. And both the Europeans and the Americans are thinking about brand new instruments that are bigger and more sensitive. If you make the instrument longer, just because as that picture, that's why I showed you the picture with the dots. If you make that pattern even larger, the dots will move even more. In fact, the amount of gravitational wave motion is proportional to the length of the detector. So one of the ideas in Europe is to take and build a 10-kilometer triangle in a mountain. That's what's going on. They're thinking in Europe, and that's what the curve goes. The Americans are thinking about building some 40-kilometer things that are L's on the surface of the Earth. And that could be built anywhere in the world. I mean, wherever there's a flat enough place. So that's sort of the way we're thinking about the future. And what we're thinking about is we would like to take this whole technology and the idea of being able to see gravitational waves and extend it into understanding the universe as a whole. And the reason why that's so exciting is because, and this is the last slide, it's exciting because we are looking at the universe in a completely different way than anything that has ever happened before. Gravitational waves go through everything. They don't get stopped. You can't look into the sun with light. Why? Because it gets scattered. The light gets scattered. You can only look a couple of 100 meters into the sun. You can't look into a star, deep inside of a star. With gravitational waves, they don't get scattered. They're very hard to detect, but they go right through everything. And so consequently, in principle, if one has the money and the energy and so forth, you could look right to the moment when the universe was born. It's a very exciting concept. And so people are thinking about that too. Now, here's the current situation in gravitational wave research in its entirety. And this is the last slide. And I just want to give you so that you know that there's more going on than LIGO. This is now frequency. I mean, it goes down to insanely low frequencies. Or up there, it's times. Age of the universe, this is years, hours, minutes, tenths to 1,000th of a second. That's the periods that are associated with these frequencies. So here's LIGO, and we've talked a lot about LIGO. Something that was planned in the United States by NASA and ESA is a mission called LISA, L-I-S-A. That's the Laser Interferometer Space Antenna. And it was designed, it's been studied about as long as LIGO. And the idea is to launch a triangle in Earth orbit in the orbit of the Earth around the sun. That's the sun. And a equilateral triangle that goes around the same orbit as the Earth does. And it turns out that orbit happens to be very good station keeping. It doesn't need many rockets to hold it there. And that it will look at, for example, the collisions of big massive black holes. Like we have a gigantic black hole sitting in our own galaxy, in the middle of a galaxy. When you look at Hubble pictures, when you look at pictures that you see in optical astronomy, you see these galaxies colliding with each other. And that means you're going to have collisions of gigantic black holes. And that's in the frequency range, which is completely different. Minutes to hours, that's in here. And that's space mission. Then there's a thing that's already going on. And by the way, just so I say a little more about this, the Americans gave up on this because of cost overruns in James Webb. But they're buying back into it, but the Europeans are going to run that mission. And that mission will probably fly somewhere in the 2030s. They're hoping to get it in the beginning of the 2030s. This is something that's going on right now. And the idea here is something different, completely different. It's going on with radio telescopes. The idea is the following. You can see gravitational waves that are coming through our galaxy by doing the following. if you look with all the pulsars, with all these stars that have these very rapid pulsing, like the one that Hulse-Taylor looked at, but they go much faster. If you can find some that really go in milliseconds, hundreds of hertz, 400 hertz. And you look at them, and they have probably several hundred of these things now. And you look at the ones in the northern sky, and you look at the ones in the southern sky, and you look at all of those, and you see what time they keep. And then you look at the ones in the east and the west, and you look at their time they keep, you'll find a pattern. The pattern is that the ones in the north and the south will all go a little faster, when all the ones in the east and the west go a little slower. That's a pattern that the gravitational waves induce in the timing of those pulsars. And that's what these people using this called pulsar timing are trying to find. And so what they may hope to find, this is now periods of 3 tens of years to fractions of a year, and they're hoping to look for a supermassive black holes. There are black holes that are 10 to the 11 solar masses, 10 to the 12. They're way early in the history of the universe. When they collide with each other, you will see these very long, very slow, slowly varying gravitational waves. And they're also looking for a background of gravitational waves that might come from the beginning. That's a little dubious, but that may be. But here's an experiment that actually is being done right now, and I only will describe it. It's too complicated. You can ask me in the questions if you're really interested. But what it is using the cosmic background radiation, the radiation that we discovered back in 1960s, which is the representative of the explosion that made the universe. I mean, you probably know that. You can listen on the radio to the early universe. By the little of the static that's between stations, especially on the FM band, is due to the cosmic background, the noise from the cosmic background radiation. That radiation has other attributes besides just the noise it makes. It can have a polarization, the direction in which the electric field points. And that direction might very well be a function of primeval gravitational waves that were generated at the moment when the universe was generated. In other words, at the moment when the universe was generated, there may have been, and a lot of people think there are, a huge amount of gravitational wave energy at very, very low frequencies was generated. Then 300,000 years after that, which is sort of the time when we look at the cosmic background radiation, density fluctuations were made in the cosmic background, in the plasma that made the cosmic background, which gave the signals a polarization. And that pattern is a very definite pattern, a sort of pinwheel pattern of the polarization. It's probably much more complicated than what you want to hear. I'm sorry. But what it is people thought they'd seen this about 3 years ago. And there was a big news item, and it turned out to have been wrong. What they were seeing is the dust in our own galaxy polarizing. That's what they were seeing. On the other hand, people have not given up on that experiment, and they're doing it right now. They're doing it with different wavelengths. They're making sure they don't get fooled by the dust anymore. And I expect that within the next 10 years, they're either going to have a positive result or a very good upper limit. So those are the directions that this field is going on in other places besides the ground-based interferometer effort. Thank you for your attention.
We have a setup on either side. If there's some questions, I'll let people get it set up for that. Before we do that, I just want to mention I'm going to plug our Carnegie astronomer. So that optical image found of that neutron star merger was from our Las Campanas Observatory in Chile by our Carnegie astronomers.
Yep.
And in fact, on September 18th, the first lecture of the fall series will be that team here talking about the kilonova. So they'll take the story where Ray left it and keep going.
Yeah.
All righty, we'll take a couple questions. Let's start on this.
Hey, by the way, when they show up, ask them why they don't see lines.
Yeah.
Okay.
The spectrographs aren't very good, but yeah, okay. Let's take a question here.
You mentioned the detector that's going to be built in Japan is going to be built in the mountain. I'm presuming that's because of neutrinos?
I couldn't understand you. I'm sorry.
You mentioned the detector in Japan that's going to be built, that's being built in the mountain. I'm presuming that's because of neutrinos?
Okay, no. I can tell you, thank you for asking that question. A lot of things I failed to tell you about. Okay, and one of them is why they want to build it in a mountain. If I had shown you that complicated picture with all the graphs in it, I would have probably way overextended your attention span. But that's where it explained. I'll tell you what the other big noise is that I haven't said. We've talked a little bit about seismic noise. But it turns out that there's another noise, which in fact the Japanese detector is trying to get away from. And what that is that if you have let's say this podium is the mirror, okay? And suppose you have a wave running in the ground that makes density changes. And the wave does that. A seismic wave does that. So let's say suddenly right here, the density of the ground has changed. This mirror will get pulled more to that side because the ground now is denser. There's more mass there, just due to Newton's theory. Newton's theory is enough to explain that. So we have another problem to worry about, not just the acceleration by seismic waves, but we have to worry about that the density fluctuations of the waves themselves make forces on the mirror. And you can't shield those. We can do a lot of tricky things like that, the seismic isolation stage, which I didn't describe entirely to you. But the thing is that you're stuck. You cannot shield it, and you have to somehow either measure it separately. And what the Japanese are hoping to do is by building that detector in a mountain, they hope to extend the ability to measure gravitational waves at low frequencies on the ground. And we're wishing them luck. We hope that they succeed. It's a tough problem. By the way, that same problem occurs in the atmosphere. The density of the atmosphere changes also because of infrasound in the atmosphere. So that pulls on the mirror also. So it turns out, I've always felt that infrasound and the gravity gradients that come from the density changes in the ground are the reason why you have to go into space. And the Japanese want to see how far you can extend the region into low frequencies. And it's admirable what they're going to do. They're going to do one other thing too. They're going to cool the detector so that there's less thermal noise. I haven't described all those different noises to you. So we're looking very much to see what the technology that they're applying, how much they really win by going into a mountain and by using low temperatures in their detector. That's the two things they're going to do.
Me?
Sure.
First, I want to say that this is one of the most intriguing and inspiring lectures I've heard. But
Okay.
I have one simple question. When you've been talking all along about the universe, you're talking about the universe, observable universe, and not what is possible other universes.
Well, okay. I think you're referring to this idea of the multiverse. Is that right? That you read about in a lot of places? That you have
monkey, you said?
multi.
Oh, multi. Okay.
Yeah. Let me just. I'm somewhat skeptical of that. Okay, and that doesn't mean it isn't true, but I'll tell you where it came from. And the idea is, it's unfortunately not provable. That's the trouble with that whole hypothesis. If you had many universes all simultaneously, okay, you ought to be able to figure out a way, at least somehow, of saying, when I see a signal, either a gravitational wave signal or a neutrino signal or whatever, I can tell which universe it's from. There is nothing that we know of where you can do that. So consequently, it's an idea at the moment with no way of testing it. And that worries me a lot. We went through many, many centuries of cosmology with that situation. Making wonderful theories up, but never being able to measure anything about the universe. We happen to be in a very interesting time right now. It's called the time of precision cosmology. You can now make models of the universe by using the cosmic background radiation and using these big telescopes like what Carnegie's building. And you can actually get really good numbers about our universe and make it a precision science. It's no longer just philosophy. And that's what worries me about the multiverse idea. But where did it come from? It comes from the idea of inflation, which is an idea that you've heard talks about here. Alan Guth gave a talk about it. And the idea that a universe can be made out of a vacuum fluctuation, a quantum fluctuation. And that quantum fluctuation can happen in your oven. It doesn't have to happen in space, and it generates a whole new universe. And look, yes, I don't know how to go any further. I'm skeptical, but it isn't mathematically impossible. Okay.
But we are at the beginning of this new cosmology. So 10 centuries, 100 centuries from now, how much more will we know?
Yeah, well, we're going to learn a lot. We're going to learn a lot about the very early. I'll tell you where the real challenges are right now. The challenges are why it's the same challenge you have in understanding what's inside of a black hole, it turns out. And it's the same challenge as trying to understand the early universe. And that's why it's so interesting to look for the gravitational radiation from the early universe, which I think is trying to be done by that's what's called the B-mode experiment, that experiment which is looking at the polarization of the cosmic background, but can also be done directly. And I hope if they get a result, I think we're obliged to argue that we should try to do this by measuring the gravitational wave directly. But what's the big problem? The big problem is nobody knows how to couple two of the most important theories we have together. We don't know how to couple the theory of gravity, which I've been talking about all night, to the quantum theory of matter. We don't know how to couple those two together. We don't know how to make a quantum theory of gravity. And a lot of people have been breaking their heads about that. And why is that important? Somewhere inside of a black hole, you're going to have to apply quantum theory when things get so small that you can't talk classically anymore. The same thing has to be true when you talk about the very moment of the creation of the universe. It's the same problem. Gravity, and in both cases, will have to deal with the quantum theory. And we don't have a good way of doing it. And that's a solution. I hope our generation, the next generation of scientists, will actually come up with a formulation of the quantum theory of gravity. It'll be a big step forward.
Thank you.
Yeah.
That's a question on the right here.
So thank you very much for your talk and for your work. I don't know if I can phrase this question intelligently, but a lot of the news on gravitational waves has been related to the detection of gravitational waves, and you mentioned the binary neutron star collision, where, as I understand it, the gravitational wave observatories, detected the event and sort of told the optical or electromagnetic telescopes where to look, and a lot of the science that came out of it that you described was from the electromagnetic telescopes.
Right.
I'm curious if what are the sort of physical problems that might be accessible only to an analysis of gravitational waves and that you can't get out of electromagnetic observation?
Yeah. Thank you for that question. That question is, in fact, at the center of why we want to continue. Okay? What he's saying is this. I mean, can I say it in a slightly different way? What the gravitational wave research, which will continue and we'll see better and better, does is it right now we are looking at things that we knew about, but in a different way. In other words, we knew about neutron stars, collisions. We thought we knew about them. Now we have really detected one. But we certainly knew about the things that go on in our universe. For example, we know about a supernova. If we ever see a supernova, which we are going to see someday with the gravitational waves, we'll know more by that one measurement than any modeling that's been done. So those are situations where we will, with gravitational wave detection, because we can look into everything, it doesn't get scattered, we can see new things about things we already know about. And I think, as you're pointing out, it's very unsatisfying, because every branch of astronomy, when it's been opened, when we went from optical astronomy to radio astronomy, for example, or from optical astronomy to X-ray astronomy, we learned new phenomena. We learned new things which we didn't know about before. And that hasn't happened yet in gravitational waves. I think the only thing I can say that we've learned that's new is that we've learned that black holes seem to live together. No, that's true. We couldn't have said that ahead of time, that you had binary black holes. But you could model that maybe. No, so you're right. The thing that we most desperately want to do, and is, I think, very much on everybody's agenda, but I'll tell you where it gets hard in a second, is to look in the data for things we don't know about. And we fully expect that we're going to see something. Now the problem comes, how do you detect that? And that's a different problem. I haven't told you anything about how we go looking for the signals. But we have two methods of doing it. One which is very much less sensitive than the other. And the one that's most likely to make discoveries of the kind you're talking about, and I would very much like to have happen, are the ones where you look for the cross-correlation between the detectors themselves without any kind of preconceived idea of what the signal might look like. That can be done, but you can only do that so well. And we do that all the time. We cross-correlate the detectors, at least, and we'll have more detectors that makes it even better. And we will learn something somewhere, some signal that we have never thought about. The way we're now doing all the black holes, and the way we're doing the neutron stars, because as we know those signals, and what we expect is we cross-correlate the detector output against a known signal. And we vary the parameters in that known signal. In other words, when we look at black holes, we make 10,000 or maybe even 100,000 templates, all with different mass black holes and spins of the black holes, and we play them against the gravitational wave detector and see which one is the best fit. And that's when we find the better, smaller signals. But that's looking for something you know, okay? So we got to do both things. And I think you're pointing out a very important thing. If there are cleverer ways, and maybe artificial intelligence techniques might be better, I don't know that, than what we have now planned, to look for signals that we don't know, but have properties that are correlated that are the same in the two detectors. That's the only thing we can go by. That's the way we'll make these discoveries. For example, I'd love to find a wormhole. You know, I mean, what would a wormhole look like? Well, for example, if we ever say, look, I'm making this up, but suppose we find that we see more black holes in one part of the sky than anywhere else. It could happen. We don't know. We don't have enough of a sample yet to know what's the isotropy, how uniform is the distribution of black holes in the sky. It'd be neat to do that, and then maybe we'll find a place where, there's a lot of them, and that will be approaching that question that the lady asked. Are we looking maybe into another universe? That sort of thing. That'd be very exciting, but we haven't come to that yet.
I know we have a lot of questions. We're going to do one more in the public forum. I'm sure Ray will be happy to answer for the rest of you guys, because there's going to be lots of questions.
Oh, well, thank you very much for the informative talk. My question is about the distance measuring techniques that you use for black holes. It boils down to is there a redshift in the signal? Because this tells you whether the energy goes down as the inverse square or the inverse cube. And if, in fact, there is redshift and it's the inverse cube, my question is, where does that extra energy go?
Yeah, let me try to rephrase your question. Do you mind? In fact, I'll show you something. And I skipped over this because I was so worried about the time. This picture right there. That picture, by the way, is close to what you're asking about. What it is, it's a picture of the following. And what it is really quite close to your question. We know all about this problem. This is the two neutron stars smashing into each other. From the waveform of the neutron stars, we know their masses. We don't know certain things. We don't know their spins carefully yet, but we know their masses. And we know how, if you take two neutron stars of known mass using the Einstein equations, we can calculate the strain that you expect at any point in the universe from that source. Okay? That's a calculation we can make. So if we know the masses and we measure and calibrate our instruments properly, which we try to do to probably 5%, we can tell you the distance that object is from us. So we have a way of getting the distance independently of the whole ladder, the cosmic distance ladder, which is so important for the electromagnetic observations. But we don't know the redshift, not yet. Now, the way we got the redshift for this pair of neutron stars is going back to that galaxy, which was now found. We know what galaxy it is, and we know the redshift in that galaxy because lines have been measured in that galaxy. And that's what this picture is. This picture is the redshift. That's the Hubble constant. I'm not going to explain it. This is now for the experts. And here are the two values. This is one value derived from the cosmic background radiation. And this value is the value, this thing is the value derived from a supernova. And this value is the value that's the probability distribution for getting the Hubble constant from the measurement of the two neutron stars, knowing what we did. And it sort of sits between them, but it's broader than either of them. When we get more of these samples, we will be able to do what's the cartography of the universe by only gravitational waves. You don't have to rely on electromagnetic waves. And that will happen once we understand the nuclear equation of state. Because as a piece of the signal, which I haven't talked about this at all, the actual waveform that occurs between the two neutron stars is not just gravitational. It turns out when they get very close to each other, the two neutron stars begin to distort each other, tidally distort each other. And that changes the waveform. And we can use that to get another force besides gravity that allows us to solve for the redshift. And so it turns out there is a whole idea that you can do all of the cartography and the mapping of the universe again entirely from gravitational waves. And it will have its own systematic errors and its own problems, but it will be a different way of doing it. And that's quite valuable because of the whole problem of how do you deal with all the systematic errors in any of these techniques. I think I haven't answered your question about every part of it, but there's a future here which I haven't described before. And this is already the beginning of it. I left that out because I didn't want to explain it all. Okay, yeah.
All right, I want to thank everybody.
Yeah.
Oh, thank you. Oh, that's for you.
Okay.
For a great talk.
Thank you.
Yep. Yeah, that's okay. Thank you for your interest and your enthusiasm for science and for coming out to our lectures. I want to also especially thank those of you who made a small donation on the way in and helped support this series. We greatly appreciate it. We'll see you all in September. Let's thank Ray again.